Hi guys, thank you for giving me the opportunity to present this work in JuliaCon 2023. So in this talk, I'm going to talk about Bayesian analysis with horseshoe prior using CRRao. So here is the outline of my talk. So first I will talk about some Bayesian Poisson regression. Then I'll talk about Bayesian logistic regression. I will briefly talk about Gaussian process models, and I'll touch upon the future work that we are doing in the CRRao package. So in the Bayesian Poisson regression with CRRao, first I'll talk about the maximum likelihood methods, then different Bayesian priors like Rich prior, Laplace prior, Cauchy prior, T-distributed prior, and horseshoe prior. All these methods and priors are also available for logistic regression and simple regressions and negative binomial regression as well. However, today I will just give you the demonstration with mostly Poisson regression. Same way you can do it using for the other regressions as well. So the first we have to call CSV data frames and CRRao and statistics package. So first what I will do, I'll call the data set from this website called footballdata.co.uk. So from this website I downloaded 2 years of English Premier League data, 2020-21 season and 21-22 season, and we will use 2020-21 seasons data to train the model and then 21-22 data for testing. In the data set you have several variables. FTHG stands for full-time goals by the home team, and this will be our target variable. So since this is the number of goals scored by the home team during a match, so it is a count data. So Poisson regression is absolutely correct kind of a model or possible. Poisson regression is a good choice to model this kind of variable. Other than that, you have different type of other variables like number of shots on the target, number of shots in the number of corners by home team, and all these things are available. So here we have little bit space constraint, but all these variables definitions are available in the website. So the first thing is read the data as a train and test. So 2021.csv is the train. We are going to read it as a train, and 21-22 as the test. Then we will consider the model. So FTHG is the number of goals scored by the home team in full time. We assume that it follow Poisson distribution. I stands for the match, ith match. In the ith match, how many goals scored by the home team, that will follow Poisson distribution with the some rate parameter mu I, and log mu I is equal to xi transpose beta, and I runs from 1 to n. N is 380. In a season there will be 380 matches that will be played. So first we will do a maximum likelihood estimates. So using CRRao and stats model, you can define your model. Just call the fit and @ formula FTHG tilde sign. HS is the number of shots taken by the home team. AA stands for number of shots taken by the away team. HST stands for the number of shots on target by home team. AST is the number of shots by away team on target. AC is the number of corner by the home team. AC is the number of corner by away team. And then I have taken two variable, which is a bit of an odd variable, but but interesting in a sense. B365 age is the Bet365 is a company, a betting company, which gives odds of winning of the home team, and B365A is the odds for um, winning for the away team. So these odds are also available before the match, so I use those odds also for the as a predictor. Then comma, you just give the data set name df train, and you have to mention the class of the model, which model class you want to fit, Poisson regression we want to fit. So if you just choose that and run it, now you can see that the p-value for HS and AS is bit small. AS is not that small, but barely 1 at 10% level of significance, but HST is definitely very small. Z value is 10. Then HC is small. Also, B365A is also small. So these predictors do have some effect, particularly number of shots on target by the home team will have a very strong positive correlation, has a very strong positive, because coefficient is also very large, 0.23, where other coefficient are very 0.0, say after first decimal, but HST is very strongly correlated with the number of goals. Now, what are the inference we found? So the following variables will have the effect on the number of goals scored by the home team. So number of shots taken by the home team, we see a positive association. HST, number of shots taken by the home team, has again positive. Number of corners by the home team, we found a negative, which is a bit of odd. And odds of Bet365 away team, which is positive. So these third and fourth observation is a bit of a questionable, what we would say, from the likelihood analysis. So the first thing we are trying is a Bayesian analysis with a reach prior. So the likelihood part is same. Now we are inducing a prior distribution on the coefficient beta. We are saying p-variate normal 0 lambda I, and on lambda we put a inverse gamma with h and h. So by default h take 0.01, 0.01, but you can, if you wish, you can choose the h as well. So now you see that rest of the in CRRao everything else is same. So defining the model, DF train, Poisson regression, same. You just need to mention prior is reach, prior underscore reach, and that's it. You just run it. The CRRao will automatically understand that, okay, you are calling for reach prior with Poisson regression. It will call Turing and it will run the Hamiltonian Monte Carlo on this model, and it will give you the results. So it was pretty fast. Similarly, we can, if you want to try Laplace prior, Bayesian regression with Laplace prior, on beta j you put a Laplace 0 lambda and lambda follow inverse gamma. Now everything else is same, only in the prior, instead of prior underscore reach, you just say prior Laplace. So now what I will do, I will just run this piece of code, and it's decently fast. Similarly, you can run Cauchy prior. The Cauchy prior, the way we have modeled it here is we just on beta j we induce t distribution with 1 degrees of freedom with scale parameter lambda, and on lambda is inverse gamma. So T distribution with 1 degrees of freedom follows Cauchy prior. So this is a prior. This is an interesting prior in a sense that it does not have any mean, variance, no moments exist. So it's a proper probability distribution, but it does not have any proper moments. So essentially, you cannot make any guess about the mean or variance about the prior. So in a sense, it's a very flat. Its tails are much flatter. So all you have to do again in the CRRao, everything else is well defined. Like, you just same model, same data set, same model class, just say prior underscore Cauchy, and that's it. You just run it. The Poisson regression with Cauchy prior will run, and it will give you the fitted model. Similarly, you can do it for T distributed prior. So T distributed with new degrees of freedom, and nu follow inverse gamma and lambda follow inverse gamma. And again, if you want, in T distribution, you have to default it. All the model runs for 1,000 simulations. But what my experience is, T distribution, you need to run a little bit longer in order to achieve a convergence. So I'll come to the convergence issue very soon. There are what my experience is, Ridge, Laplace, even Cauchy will give you a nice convergence, even with 1,000 simulation, because these uses a Hamiltonian Monte Carlo, which works much better than simple Markov chain Monte Carlo. On the contrary, T distribution and horseshoe prior is bit, you need to run a little bit more. So here what we are doing, we are saying that okay, Poisson, it's my target value variable follow Poisson and this likelihood, and then each beta j follow normal 0 lambda j tau, lambda j follow half Cauchy with 0 1, and tau follow half Cauchy with 0 1. So lambda j behaves like a local shrinkage for that particular, for coefficient specific shrinkage, whereas tau follow a global shrinkage. It's control the global shrinkage of the entire model. So this is a very interesting prior. So again, all you have to do, the same model, same just training up to this, you are exactly same. And then here you just mention prior underscore horseshoe, and then 1,000, just 10,000. I am default is 1,000, but I made it 10,000 so that it runs quickly, and it runs a slightly longer chain and gives, hopefully we will have a convergence. If we don't face a convergence, then what will happen is we have to run it again. So this is a bit of a painful process. You may have to run to like maybe 20,000, 30,000 simulations, which doesn't take much time. It's for a moderate size data, it might take 5 to 10 minutes, but it does decent job compared to if you run it in say R or Python. So okay, it's done. Now I'm saying that okay, show me the model performance. Okay. Okay. So what we are seeing, so you can see most of these R hats are very, very close to 1. Since most of these R hats are very, very close to 1, so we can we can say that yes, looks like this horseshoe prior with 10,000 simulation, Monte Carlo simulation from Hamiltonian Monte Carlo chain has worked reasonably well. And when I did the analysis, and then what we found with the Bayesian Poisson regression with the horseshoe prior is the home number of shots taken by the home team was positive. It was same as likelihood analysis. Number of shots on target by home team was also positive, and it was same as likelihood analysis. Number of corners by home team was negative, same as likelihood analysis. What we found that odds of bet 364 for away team does not have any effect. In likelihood analysis, we found that bet 364 does have a positive effect. So this is a interesting way. It's typically what happens in with the horseshoe prior. If a particular coefficient does not have an effect, does not in likelihood analysis might show some weak effect, but with the horseshoe prior you will find that it will be get rejected, and in fact it will be like it will not, you will not find any effect for those kind of weak effects. So if you do the plots of the chain, okay, so what we are seeing here that, so remember that the chain has converged for the lambda. This is the tau nicely sort of a chi-square type behavior. These are the lambda values, and they have a very kind of thing. Now here is the beta one, the intercept is like, and this is, you will always find like something is not does not have an effect, will have a very sharp sharp mode at 0. So, and that beta 2, which is probably home team shots, is complete, has an effect, so it is completely on the negative side. Okay, then beta 3 also sort of almost like negative side. Beta 4 is completely positive. Okay, now beta 5, you can see a very sharp positive mode at 0. So that means beta 5 does not have an effect. Similarly, beta 6 is almost mostly in the negative region. Beta 7 also very sharp mode at 7. Anybody which has a sharp mode at 0, we can just drop them from the model. So this is typically, so here beta 9 looks like it is inside the 95% confidence interval. So this is how, so that means that this was the beta 365. So we can say that yeah, it looks like does not have any effect, so we can drop them. So here I have done a small model for Poisson regression with the horseshoe prior. And if you just plot them, so here is the full model. So you can say this is the intercept, which is a negative sort of behavior. This is the negative, this is positive, and this is negative. So what we are seeing that it has some, when we are considering a short model, its direction is getting changed. So this is always often happens that the direction gets changed, that means the interpretation gets changed, and this is always a problem with a typical statistical analysis. So this is, here is the statistics plot, all the statistics plot you can see. Now based on this model, I did a prediction on the test data set. Okay, now I did a predict. All you have to do, just call the model, whatever model you want to work on, call the model and provide the test data set, it will do the prediction. And then if you run this, so here is the prediction for 380 matches, test matches or the 21-22 season, all the seasons matches are here. So there is the approximated R squared that we have calculated here, 31.7 or 32% R square. and then we also calculated RMSE, so 1.14, and then we did a plot. So if you see the plot on the x-axis, we plot the predicted goal by the home team. On the y-axis, we plot the actual goal by the home team. So what we are seeing, this particular model is doing a bit of a overestimation. So because there are these goals, if you see these goals are in the range of 4 to 7, whereas the model is predicting 5 to 10 or 11. So similarly, these goals, these cases, these matches, the number of goal is somewhere in the range of 2.5 to 5, and whereas they are mostly in the range of 2.5 to 5. But at the same time, here these cases, you can see the prediction was somewhere in the between 0 and 2.5, whereas home team did score a bit of a underestimation has happened. So some cases it was underestimated, some cases it was overestimated, but looks like there's a slight chunk behavior of overestimation is happening. So now we will move to the logistic regression analysis with Friedrich-Achia data. So it is a bit of an old data, but it's very popular, available in the R dataset package also. So from the R dataset, we will call this data. So from our dataset, you call the GPA package, from the GAP package, GAP package, the AFA dataset. And if you just run this, so this is the dataset. So this is the Y value. These are all coded as 0 or 1. And there are 12 loci from 1 to 12. They are codified. They are all typically integer. So here I have written a small function to split the dataset into train and test. So run this, and then split the dataset with 70% for the train and 30% for the test. So here is the train dataset, and here is the test dataset. Okay, you got a test dataset. So now if we want to run the maximum likelihood estimates, all you have to do formula y and give all the y tilde, and then give the all predictor variable, then give the training dataset name, say name the logistic regression, and say logit. So if you want probit, then it can call it probit. If you want a Cauchy link, you will give a Cauchy link. So there is a bunch of links are available, link functions. So you can we just use the logit link here. So you can see here the loci 3 may have some effect. Okay, loci 3 may have some effect, and rest of the loci does not have any effect. Loci 11 may have an effect, some kind of weak effect at 10% level. Loci 12 definitely have some kind of effect. Okay, so loci 3, loci 11 and loci 12 looks like have some effect based on simple likelihood analysis. Now, so that is what I have written. Loci 3 and 12 statistically significant even at 5% level, maybe at 1 even, yeah. And loci 11 significant, maybe at 10% level, we are not so sure. So if I do a prediction based on this, and if I run this, this will give me the confusion matrix. So first 2 is 0 and 39 gives me all. So my test data is such that it gives all 39 negative values, and then 21 and 18. So 21 true negative and 18. So everything false positive were given. So if you change it to 0.5 to 0.7, then you can see that it has 21 to 29 true true negative has gone up from 21 to 99 and false positive has come down. So this is now similarly for this model we can apply Bayesian logistic regression with horseshoe prior. Yi follow Bernoulli pi, and pi we have taken logit mu I. Mu I is xi transpose beta, then beta j follow normal 0 lambda j tau, where lambda j is the local shrinkage and tau is the global shrinkage. Now lambda j follow Hop-Cauchy distribution and tau follow Hop-Cauchy distribution. For each coefficient we have a lambda j and it plays a role of local shrinkage. Same model, almost no problem. All you have to do is just call the fit formula, provide the formula, train logistic regression logit, and then just mention prior horseshoe, and then you are done. So and then if we just say show, so what we are seeing that we are not facing much of a problem. Most of the R hats are close to 1, so I'm sorry, I think the font is bit of a small problem, but most of the ones there is 1.3 is there. So if you want to make sure that it is run, it is absolutely converged, then you may have to run once more. So let me just do a plot. So you see tau and all these things may have, looks like it may have some convergence issue. So lambda 1 11, looks like it has. Beta 0 is absolutely very sharp, beta 3 is here, beta 3 is bimodal, has become bimodal. So maybe we think of running it once more. Let's go back and run it once more. Let's run it once more and see what happens. So if it runs once more, it doesn't start from the scratch. It actually keeps the history and it uses it. So essentially you are starting from 11,000. Okay, so now if you run it, okay, and maybe, so okay, now it is bit of a, so as I said that convergence is always a bit of an issue, so you may have to run it for a while. Now looks like it has converged. Yes, looks like it has converged. This is beta 1. You can see beta 1 is all 0, and then beta 2 is also very sharp mode at 0. Beta 3 also made it 0. Beta 4 is not 0, looks like entirely positive. 5 is have a very sharp mode at 0. Beta 6 also have a sharp mode at 0. Beta 7 has a sharp mode at 0. Beta 8, beta 9, 10, everything has a very sharp mode at 0. 11, 12, see 13 does not have any sharp mode at 0. It is completely negative. So as we discussed that so 3, 4 except 13, it turns out everything else has a very sharp mode at 0. So now finally, I would like to discuss a little bit about Gaussian process regression. We are implementing Gaussian process regression, and we are just now doing some tests. The implement development is completely completed. So we are using Gaussian process package in Julia, Gaussian processes.jl. And what our plan is, basically by end of this month, I hope it will be integrated and it will be released. So now from the our data set, we are calling the empty cars data set. Okay, and all you do, just provide the formula, provide the data set, and then call the Gaussian process regression. That's it. If you run this, then it will do the analysis for you. So target variable is miles per gallon, and weight is the index variable. We will be consider weight as index variable. And if you draw this model, we ask the plot, so you can see the plot, weight is x-axis, and on the y-axis we plotted the mpg, and it fitted a nicely nonlinear regression with a 95% confidence interval for the curve. So it is very nicely done. So this will become very useful for a daily analysis, somebody who wants to do a simple nonlinear regression. So currently we are going to implement it. We are planning to integrate ARIMA from statespace.jl, k-means clustering, mixed models.jl, stepwise. There are some students who are working on stepwise selections, variance inflation factors, and Bartlett's rank test. So here is our GitHub page on CRRao. Please do support us, star us. That will be a very helpful. And thank you very much.
Yeah, so for questions, you can connect with me or you can email him, message him on Slack. I think that would be the best. I may not be able to answer these questions. So that's all. This is the end of the symposium. Do not come back at 2 p.m. That's all.